All right, got that going, and I think we're ready. Okay, so now we finished up calculus, and today we are going to be starting physics. A little bit of bookkeeping. I was pretty nice to you guys with calculus because technically you didn't have all the prereqs you needed. Like neither of you had taken trig, for example.
Yeah.
And so I was very nice to you in calculus because you didn't technically have all your prereqs. I'm not going to be as nice to you in physics when it comes to grading things now. Now you have the prereqs. Calc, that's the only prereq.
Okay.
So you got the prereqs, everything else is covered in this class. So I'm going to be a little bit meaner in this class in terms of grading and not just giving you bonus points on stuff. So there's that. Second thing you'll notice in this class is way less homework, but the homework problems are much harder. Here's how, I know this is a lot of work. You're going to notice you have way less homework problems than you did in calculus. They're just going to be harder problems. This is one where reading the material is so useful because the point of a homework problem is to test to make sure you understood the material. You're not supposed to go read the homework problem, look back at the material, see if you can figure out how to do the homework problem, then do the homework problem. You're supposed to go through the material and see if you're able to just do the homework problem afterwards to make sure you understood the material. Physics is very conceptual. It's not just, here's the next formula that you need to memorize, or here's the next formula that you need to memorize. You're going to notice in this book, we do give you a bunch of formulas as we go through, and at the end of each chapter, the author highlights, here's the important formulas to memorize. But if you try memorizing all these formulas, you're going to get in trouble. And you're allowed note cards and stuff like that on your test, so I would, if I were you, start keeping a note card of the formulas at first. But with time, hopefully, you don't have that heavy reliance on the formulas. And well, you'll see some of that pretty soon. Your understanding of calculus, you'll already see how that helps you deduce a bunch of formulas really quick just by integrating, as opposed to having to memorize. Anyways, so what's the big difference now between calculus and physics? Because calculus is what Newton developed in order so that he could do physics. He started at, that's when calculus came as a thing. He discovered calculus so he could solve physics problems. But what's the difference between calculus and physics? It's the difference between a math and a science. So we're shifting now from a math field to a science field. What do we do in a math field? We start out with our axioms and we just look at their logical implications. Now I don't know in calculus if we listed out all the axioms on the real numbers, but there's a set of axioms on the real numbers and all we were doing was looking at their logical implications. Now we were focused on application of calculus, so we didn't focus on just proving things from the axioms. That's called real analysis. That's typically how I teach calculus. But specifically I taught it this time so that we could prepare you for this class. But that's what you were doing, and that's what you do in every math class. You start with axioms and you look at their logical implications, right?
Yeah.
Well, in physics, or in a science in general, but particularly in physics, we can no longer do that. We don't just pick an axiom and say, we'll just assume that's true. Our axioms, our basic assumptions, our postulates need to somehow relate to this universe. That's what we're interested in. Mathematics is in no way contingent upon this universe. This universe ceases to exist, calculus is still as true as it ever was. If this universe ceases to exist, all the physics goes out of the universe too. Physics describes this universe. And so we need to start by describing this universe. So how do we get those basic postulates for our universe? We need to reason our way to those basic postulates. Now let's remind ourselves of the three basic types of reasoning. There's deductive reasoning. This one you're now the most familiar with. It's just logical implications. If all men are mortal, and if Socrates is a man, then
All men are mortal. Socrates.
Socrates is mortal. That was used in deductive reasoning. The two premises imply the conclusion. Deductive reasoning. Inductive reasoning is the reasoning of it always happens. It's the reason you think that the sun will come out tomorrow. You didn't deductively prove that the sun will always come out. Why do you think the sun's going to come out tomorrow? Because every day of your life the sun's come out. It's inductive reasoning. Same reason you think that if I grab this thing and I drop it, it will fall to the ground. Every time you see an object drop, it falls to the ground. That's inductive reasoning. You with me? Mm-hmm. And then, again, abductive reasoning. This is the least precise type of reasoning. That's just basically the reasoning of a best guess, reasoning beyond reasonable doubt. Type of reasoning that they use in a courtroom. In a courtroom, they don't prove that every time this situation's come up, this is exactly what's happened. They don't inductively reason to their conclusion. They don't do it. Well, I won't say that yet. So those are roughly the three types of reasoning. So how does a field of science begin, and particularly how does physics begin? We inductively reason. So inductively reasoning to premises,
Okay.
determine their implications, and then testing their implications. That's roughly what you do in the field of science. So first, inductively reasoning to premises. How do we do that? Not only do we inductively reason to our premises, we inductively reason to our premises based on observable fact, or quantifiable phenomena. It has to be quantifiable, it has to be measurable. So I could take this thing, and I can measure how it falls, how it falls, how it falls. Carefully measure the acceleration of this thing as it drops every single time. And if it looks like it's always the same, I now create a premise. Objects accelerate downwards at 9.81 meters per second squared. If I keep measuring it and it looks like it keeps coming out that exact number. Does that make sense?
Mm-hmm.
So that would be a basic premise that we operate on. Something like acceleration equals 9.81 meters per second squared. And then we know what velocity is. Velocity then, by definition, is going to be the integral of acceleration.
Yep.
So that's a logical implication now that v is equal to 9.81. We're going to integrate with respect to times plus a constant we call v naught. That was a logical implication of this. So now I have some sort of abstraction, some sort of model that describes velocity. So now I can go back and drop this thing, and now instead of measuring its acceleration, measure its velocity. And see, do I get this? Is this what happens? If it is, then we've got a good model. If it's not, then we probably did something wrong and we need to restart. Does that make sense?
Mm-hmm.
That's roughly how the scientific process works. So we inductively reason to our premises based off of observable fact or quantifiable phenomena. You have to be able to quantify it. You have to be able to measure it in somehow. It comes back to measurement. The things we can measure are the things we inductively reason on. If you can't measure it, we don't talk about it. How does this piece of chalk feel? Is it happy? We can't measure that. So physics has nothing to say about that.
Okay.
Make sense?
Yeah.
Okay. So it has to be measurable phenomena. The things that we measure are times, lengths, and masses. We'll add to this list. We'll start out with just these three. But in general, for the majority of this class, all we're interested in is measuring is time, lengths, and masses. And typically we measure time in seconds, we measure length in meters, and we measure mass in kilograms. As a general rule. So for example now, first off, that makes sense with measuring just a distance, right? How do I measure area?
Length times length.
Length times length. So it's still just using lengths. So if we were measuring area, that's meters twice. So that's meters squared. So that's using length twice. And if I were measuring volume, we could do it in meters cubed. That's measuring length 3 times. What's some other things we can measure? We can measure speed, for example. What's speed?
Time times length. Meters per second.
Meters per second. It's meters, it's length over time.
Oh.
I can go 10 meters in 2 seconds. That's giving me a speed.
Okay.
An acceleration, this one might not be intuitive to you yet, but it's meters per second squared, it turns out. And then I can tell you something like force. This one won't appeal to your intuition. We'll come across it, but you'll just have to take my word for it. Even something like force. What's the units of force? It's kilogram meters per second squared. And there's no reason for that to appeal to your intuition. But so all we use are seconds, meters, and kilograms. All we measure are times, lengths, and masses until we get up to charge. That will be electricity and magnetism. But so basically for this class, this is all we'll be interested in. And all the things that we measure are combinations of just lengths, times, and masses.
Okay.
Make sense?
Yeah.
And so if you can't apply these things to it, it's not physics. We're interested in measurable phenomena. You have to be able to measure it, and these are the 3 things we measure. A little bit of a side note. It's not important, actually. We don't worry about that. Okay, so give you a rough idea of science, what science is. We inductively reason to some premises. We determine their tautological implications, their logical implications. And then we test those implications back in the real world. That's roughly what we do in a scientific field. So how does physics relate to all other sciences? And how can you kind of get a rough picture of what the fields of sciences look like in your head? And you can kind of get that with roughly this pyramid right here. So this pyramid, anything above presupposes everything below. It's built on everything below. It assumes everything below. So you start with logic. Then you build math from logic. You didn't get to see that, but we did that in topology. We start out with logic and we built set theory, which is the foundations of every field of math.
Yep.
So logic, you use logic to construct math. And now we use math to describe physics. So physics presupposes math and logic, and that's it. It's the most fundamental science. It's at the foundation of all science. And then physics is at the foundation of chemistry. So chemistry presupposes physics, not the other way around. And biology presupposes chemistry, not the other way around. And if we put some social science up here like psychology, psychology presupposes biology, not the other way around. Another way to think about physics is if you keep asking the question how something fundamentally works over and over again, you'll eventually reduce your question to a question of physics. So, for example, take some biological fact. Humans get energy from food, right? Mm-hmm. Okay, so then you say, how do humans get energy from food? How does that actually happen? And then you might learn about some of the cycles that go on in your body in terms of the chemicals that are broken down, how it's turned into a sugar. But eventually you'll learn about this molecule, ATP. And that's one molecule that's part of you getting energy. It's roughly the energy molecule. And then you might ask the question, okay, but how exactly is that ATP formed? Okay, now that gets us back into chemistry. And so we've got to talk about the chemistry that goes on inside the mitochondria, inside of a cell, the electron transport chain, for how ATP is actually created, this little energy molecule. And the chemist will tell you. He says, okay, yeah, but how does that electron transport chain actually work in constructing this thing? If you keep asking the how, you're going to get on a low enough level that now we're talking about physics. So it's fundamentally what underlies every question. If you keep asking the how, you want to know how it fundamentally works on a fundamental level, it's going to come back to physics. Physics is the most fundamental of the sciences. Every science ultimately reduces to physics. Okay, make sense?
Yeah.
Okay, so that's roughly where physics stands. It's the most foundational science. And just terminology, we call these three sciences the low-level sciences, and then these sciences above them higher-level sciences. And it's because of what they presuppose that they're called a low-level science or a high-level science. So physics is a lower-level science, and chemistry is a lower-level science than biology. And that's where those terms come from.
Okay.
What presupposes what? So we're interested in physics, the most fundamental of the sciences, the most foundational. All right, and we already mentioned physics, we're only interested in observable or quantifiable phenomena, things that we can put some metric on, some number to. We can say this many of some unit. Now, units are crucial in describing things. You need to use your units. We get pretty lazy, especially me up here on the whiteboard, because I'm talking and sometimes I just say the units out loud a lot, but you need to put the units. If I say that thing is 19 long, what does that mean? How tall are they? Oh, they're 19. 19 what? So you need your units. Are they 19 meters, 19 inches, 19 centimeters? We need units. Otherwise, the number is meaningless. So the quantity needs a unit associated with it, always and forever, in every answer you ever give in this class. You need units. All your answers should have units. A number by itself is meaningless. That tells me nothing about the real world. It's a number together with a unit that you're now saying something about the real world. Why is that? Because these units exist somewhere in the real world. Now, it's not the way it's currently done, but we'll go back to the way it used to be done. For example, a meter. What was a meter? There was a platinum rod over somewhere in Paris that was, by definition, a meter. What's a meter? It's how long that platinum rod was. So when you say something's 2 meters, you're saying it's 2 of those platinum rods. So you say 2, and then you tie it to something in reality. It's 2 of those platinum rods. That's how long it is. So the units are what tie the number, the quantity, to this universe. Because you're talking about something physical in this universe. That's how the units are defined.
Okay.
Now, it's not how we define the meter anymore. We define it as the amount of time or the distance light travels in a very, 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 very small amount of time. But it's basically the same thing as that platinum meter stick. So we just come up with more precise ways of talking about them. But it's still relating to physical phenomena in this universe. Our units always do, always will. And that's what ties it, a number, to this universe. The unit. So units are crucial. Understand the units. Okay. Now some unit prefixes that you're going to see all over the place and what they mean. Starting out with nano. Nano is short for 10 to the negative 9. Okay? So if I say a nanometer is 1/1,000,000th of a meter.
Okay.
10 to the 9 is billion. So 10 to the negative 9 is 1 over 10 to the 9 is billionth. So a nanometer is 1/10000000th of a meter. So we represent that as 1 nm is short for nanometer is equal to 10 to the negative 9 meters. 1 nanometer equals 1/10000000th of a meter. Does that make sense? Mm-hmm. Okay. Another common one is micro. Micro is a millionth. You with me?
Yeah.
Now, 1 micrometer is equal to 1/1,000,000th of a meter. Now we use mu, a Greek letter there, instead of a little m, because little m was already used for millimeter. So that's why there's a weird u there instead of m.
Okay.
You with me?
Mm-hmm.
So that one's a little off. You have this table in your book, just so you know.
Oh.
You can write down if it helps remember. I just making sure you know. You guys have your books, right?
Online.
Yeah. Okay. Yeah, make sure you got your books. Okay. Now, milli is thousandth. So 1 millimeter is equal to 1,000th of a meter. Good?
Mm-hmm.
Centa, or cent, probably, is hundredth. That's why we call 1/100th of a dollar a cent. Cent is hundredth. 1 centimeter is equal to 1/100th of a meter. And then finally, kilo is 1,000. 1 kilometer is equal to 1,000 meters. So here's some of them. There's more. These are the ones that come up the most. So good to be comfortable with them. Make sense?
Yeah.
Okay. So now, here's where we need to have that discussion about getting a feel for these numbers. Getting a feel for how big or how small one of these numbers is. How small is something like 10 to the minus 12, or how big is something like 10 to the, what did we do before, 16? So before we pull up this video and get a sense of both these, I want you to pick something just roughly in your head, something roughly of what you think 10 to the 16 meters is roughly the size of, and what you think 10 to the minus 12 meters is roughly the size of. You're not being graded, just roughly what appeals to your intuition.
I like the Earth.
So we'll do Earth, meaning there the circumference
Yeah.
for that one. Okay, what about for this one? Is that like the width of a hair? Is that like a cell?
It's like
That's like an atom? Like a big atom or a small atom? We talking about like hydrogen, or are we talking about like uranium? Doesn't matter. So we'll stick with, we think this is roughly the size of an atom, and we think this is roughly the size of the Earth? Or do we want to change this one? Or do we want to change this one? We like it?
I like it.
You like it?
I think it'd be bigger than Earth.
You think bigger than the Earth? What do you think?
I'd be more like Jupiter.
Jupiter.
Okay.
So we'll just do planet. Some planet.
I like that much.
Maybe a really big planet. Not quite the size of a star, but maybe a big planet.
Yeah.
Okay.
Good? Okay, so now we turn off the lights. And hopefully we can see this.
You want both of them off?
Yeah, it's on a dark background, so I think it's going to be hard to see otherwise. Can you see that all right?
Yeah, I can see that.
Yeah.
All right, so we're going to start it by zooming out. So right here, this is 1 meter, that circle's 1 meter, or 10 to the 0 meters. 10 to the 0 is the same thing as 1. Then we're going to look at things that are 10 to 1 meters, 10 to 2 meters, etc. and get a feel for this. So we're now zooming out. So giant earthworm, big crab, there's an elephant, a nice big tree, some massive dinosaur, Boeing 747, some massive redwood tree, football field, Eiffel Tower. Okay, now we're at 10 to the 3, so here is a kilometer, or 1,000 meters. Right?
So all that stuff can fit inside of 1,000 meters?
Yeah, so that's to scale. So if this were 1 kilometer, then the Great Pyramid would be that tall, or the Eiffel Tower would be that tall, or Hoover Dam would be that tall.
Okay. Okay.
All right, so we keep going. Some tall buildings. Now we're starting to get some big rocks floating in space. Central Park there, that's in New York. There goes Mount Everest. Some other big rocks. Some really small moons. West Virginia, the state. And now we're at 10 to the 6 meters. So 1 million meters. So here's West Virginia, the state. There's the Grand Canyon. Here's 1 million meters. And you can see California there to the left. All right, keep scrolling out. All right, there goes the Earth.
Wow, Earth doesn't
The Earth, notice that we're at the scale now of 10 to the 7 meters. There's the Earth right there. So, good thing you didn't pick that one, because we said 10 to the 16. There's Venus, there goes Saturn, Uranus, oh not Saturn, Neptune, Uranus, Saturn, Jupiter, a bunch of other planets, stars, moons. Now we got into the sun. There's the sun. This is 10 to the 9 meters. Here's the sun. And we said 10 to the 16, so not even the sun was there. Maybe the solar system? We'll see. So there goes the sun. Here's a bunch of other massive stars, even bigger stars, even bigger stars, even bigger stars. Distance from the Earth to the sun right there. Wow. And we are now getting to 10 to the 12 meters. And still even more massive stars. It's amazing the variety in star size. Distance from Neptune, the furthest planet to the sun, is right there. The Kuiper Belt, so there's our solar system. One light day, that's how far a photon goes in one day. Distance, let's see. So 10 to the 15 meters, and now we've got a little nebula here, which is roughly 10 to the 15 meters. So 10 to the 15, and 10 to the 16 is roughly right here. So 10 to the 16, roughly a light year. How far light goes in 1 year. It's as big as some nebulas, smaller than other nebulas, not quite the size of a galaxy, but bigger than some nebulas. What's 10 to the 16? And the Earth was roughly, when did we see the Earth? At 10 to the what?
10 to the 7.
10 to the 7? So you were off by 9 orders of magnitude. The Earth is 1/billionth the size of 10 to the 16, roughly. So, by the time we get to 10 to 17, do we have any galaxies yet? No, still just nebulas. Nebulas. Okay, coming up on a galaxy, so a dwarf galaxy at around 10 to the 19. And then we get some bigger galaxies, Milky Way galaxy comes in close to 10 to the 21, which is the galaxy we're in, with its billions of solar systems. And then eventually we get to groups of galaxies, 10 to 24 galaxy clusters. One gigasec. And we zoom out, and here's roughly the observable universe. So the observable universe is roughly 10 to 26 meters. So at 10 to 25 meters, when we're talking about massive clusters of galaxies, the difference between that and 10 to the 16 is the difference between 10 to the 16 and the Earth. Okay, so now let's zoom back in and let's go the other way. We're looking at 10 to the minus 12 now, right? So there's 1 meter. Now we're zooming in. Small things, penny, matchstick, microwave wavelength. And there goes an ant. And now we're at 1 millimeter, 1,000th of a meter is right there. So an ant's a few millimeters across. Right? Zooming in more, there's the width of a human hair right there. Here's the thickness of paper. Infrared wavelength. So that's the wavelength of light, that's infrared. Width of a silk fiber right there. Mist droplet right there, white blood cell, red blood cell, chloroplast, X chromosome. Okay, here we are 1/millionth of a meter. There's a virus right there, some other virus right there, violet light wavelength. Zooming in some more viruses. There's actual DNA. This is what your cell membrane is made out of. So that's like opening a cell membrane. Zooming in more. All right, so here's an atom, which is at 10 to the minus 9.
That's why I just said atom. It'd be a smaller one.
Yeah, we'll zoom in more. Here's a water molecule. Here's a carbon atom.
Oh wow.
And then a hydrogen atom and the helium atom. Those are your smallest atoms. And we're at around 10 to the minus 10. So not too bad on this one. Here's 10 to the minus 12 right here. So let's see what's roughly on that scale. Nothing. The gamma ray is almost on that scale, roughly, yeah. Wavelength of a gamma ray is roughly 10 to the minus 12. So you're only off by a factor of 100 on that one. Not bad. Zooming in more, we get 10 to the minus 13 and start to get the nucleus of a uranium atom, nucleus of a hydrogen atom, an electron. Proton, neutron.
Make sure this is not
Zoom in even further, so now we're at 10 to the minus 18. We got up quarks, down quarks. Those are what make up protons and neutrons. And then different types of quarks that you wouldn't know anything about. High-energy neutrino, you wouldn't know about neutrinos. Top quark at 10 to the minus 21. 10 to the minus 23, neutrino. Keep zooming in, keep zooming in, keep zooming in. 10 to the minus 26, to the minus 27, to the minus 28, to minus 29, to the minus 30, to the minus 31, to the minus 32, to minus 33, 34. And then we get down to some of the smallest things we talk about in physics, a Planck length, which is the smallest meaningful distance. And then there's roughly what a string, the size of a string from string theory, and then quantum foam, you wouldn't know what that is. But Planck length is something that you'll come across in physics too. So that's roughly the smallest distance that we talk about. So notice that we go on 10 to the minus 34 in terms of lengths is the smallest lengths we talk about. And the biggest lengths we talk about are, keep going. The biggest lengths we talk about are 10 to 27, which is the observable universe. So what was the negative one? 10 to the minus 24, or 34? 34. So we go, kind of a funny way of saying it, we go 10 million times further in smallness than we do in terms of bigness when we talk about sizes of things. But anyways, there you go. So that gives you a rough idea of different measurements of things, and physics is interested in every single one of those things. Talk about everything from the observable universe all the way down to strings and plane planes. And as a general rule, general relativity is interested in the very big things, and quantum mechanics is interested in the very small things. Anyways, that's all we need this for. Oh, I did not move the camera. I can't believe you guys let me not move the camera. You should have done my squiggly line. All right, don't let me go to the whiteboard without moving the camera. Yeah. Okay, so now, let's talk about making things dimensionally consistent. Dimensional analysis. Okay, so solving physics problems now. I already pointed out to you how important units are. When you're solving physics problems, it's often very useful to do a quick dimensional analysis on your physics problem as a sanity check. And that's to make sure that the units come out the way that they ought to come out. So the simplest example of this is going back to some of the earliest physics problems you ever did back in algebra class. They told you length times time, or velocity times time equals distance, or speed times time equals distance. I don't know exactly how they said it, but they told you that a speed times a time gives you a distance, right? Well, what's a speed measured in terms of?
Distance over time.
It's distance over time, so it's like meters per second, right?
Yeah.
So when I take meters per second and I multiply it by a second, what am I left with?
Just
Meters.
You're left with meters. Make sense?
Yeah.
So what we did was dimensional analysis really quick to make sure what we were multiplying together made sense. So a speed times a time does give a distance. And that right there is dimensional analysis, doing stuff like that. Or velocity times time gives us a distance. So that's a super, super simple case, but the point is there'll be problems that you go to solve, and you won't be sure. You're like, maybe if I multiply these two things together, that will give me the answer I want, right? Before you even start computing it, just check the units. If I take these units and multiply it by these units, does it spit out the units I want? Or if I take the units and divide by these units, does it spit out the units I want?
Okay.
So that's where dimensional analysis is really helpful. It helps you make sure you're on the right track before you start all the heavy work of actually doing the computations. Okay, we talked about that. So now let's do some conversions. Really quick, and we need to talk about significant figures. So first we'll talk about conversions. And pay attention to the units as we talk about conversions. So we're going to convert 763 miles per hour to meters per second. You with me?
Yeah.
So I'm going to write out the first grader way. We'll do it the first grader way once, and then after that I'm done doing it this way.
Okay.
So you can always do it this way to help you make sure you're doing things right. It's very tedious, so I'll hardly ever do it this way. Anyways, so we have 763 miles, MI is what we typically use for miles, over 1 hour. You with me?
Mm-hmm.
Now I want to convert this to meters per second. That's what I'm about to do. Now when I'm manipulating a number, and I don't want to change the number, there's only two things we can do. We can add 0 and multiply by 1. Right?
Yeah.
For converting units, we're going to
Multiply by 1.
multiply by 1. So, how am I going to get miles and to hours into meters per second? Well, first thing I can do is convert the hours to seconds.
Yeah.
Right? That's an easy one to do. So I can multiply this by, there's 3,600 seconds in 1 hour. 60 times 60. There's 60 seconds in a minute, 60 minutes in an hour, 3,600 seconds in an hour. You good with that?
Mm-hmm.
And so based on the units, notice that that's just a 1. We're just multiplying by 1. We didn't change the number.
Yeah.
Don't you want to switch your hour and seconds, or does
Oh,
it
thank you.
matter?
Yep, you are 100% right. Oh, did I just do the same thing twice? There's 1 hour. Okay. Wrote it wrong twice. Where are the odds? All right. So that got our hours now to seconds, right? When I multiply this out, I don't care what the number is right now. Notice hours cancels out with hours, and so we'll get miles over seconds. So this will give me miles per second.
Okay.
You with me?
Yeah.
But I want meters per second. So I need to convert miles to meters. Now I don't know how to do directly miles to meters. What I do know how to do is I know how many feet are in a mile. You know how many feet are in a mile? 5,280 feet are in 1 mile.
Okay.
And now I know how many inches are in a foot. I know that there's 12 inches in 1 foot. And now I know how many centimeters are in an inch. There's 2.54 centimeters in 1 inch. And then finally, I know how many centimeters are in a meter. 1 meter is the same thing as 100 centimeters. You with me?
Yeah.
So now when we multiply out this whole thing, first we'll start with the units. Notice hours crosses out with hours, miles crosses out with miles, feet crosses out with feet, inches crosses out with inches, and centimeters crosses out with centimeters. So in terms of units, I'm left with in the top meters, and I'm left with in the bottom seconds. So my answer is going to be in terms of meters per second.
Which is what you're looking for.
Which is what you're looking for. And now, what do? You just need to multiply all the numerators and divide it by the product of all the denominators, and it comes out some number. This is where I strongly recommend that you get a calculator, because you will be doing this all the time in every problem. You'll need to be able to hurry up and make these calculations. You are allowed a calculator on all your tests. You are encouraged to use a calculator on all your tests. It makes life a lot easier. So now we need to do 763 times 5280 times 12 times 2.54 is equal to that divided by 3,600. And I must have messed something up.
It's 3,600 times 100.
Oh, thank you. I was going to say, I'm off by a couple orders of magnitude. All right. 340.1. They do 341. Yeah, good enough. So, 341 meters per second.
Do they not have like the formulas for doing that easier?
This actually isn't that bad to just do in your head. Because first you convert miles to meters, and then you convert hours to seconds. And so you just type it out on a calculator. Why memorize a formula? Oh, it might have been weird to you that I had all these numbers memorized. Is that what's weird?
No,
Yeah.
that makes sense. I knew the miles and centimeters just easy. But like,
Why memorize something else when this is such an easy calculation?
isn't there just a numerator number over denominator number you can multiply to make that work?
Yes.
So you don't need to multiply it by 5,280 and 12 and 2.54. When you can just multiply.
Ignore the 763. So take this, 763. That's miles per hour. I could just multiply all these things together and memorize that number, and then I'll just multiply by that number whenever I want to convert miles per hour to meters per second.
So what's that number?
It's that divided by that.
I'm saying, why do you write it out every time? You just memorize it.
Because you're not always converting miles per hour to meters per second.
Yeah, that's a lot of memorizing.
You don't want to memorize every combination. You just want to know how to calculate it.
Okay.
Because what if I gave you 763 miles per minute? Now you need a whole new number. What if I gave you 763 miles per second? Now you need a whole new number. So it's easier to just know how to calculate it. All right, another conversion. This one dealing with something cubed, because that often gets students. So again, we'll do this the first grader way one time, and then we'll never do it this way again. So we are converting 1.83,
8-4.
thank you, 84 inches cubed. So I have some volume of water or something like that, and I know it's 1.84 inches cubed. That's its volume. I want to convert that to centimeters. I think that's what we're doing. To centimeters. Okay. So we need to convert that to centimeters. All right. What can we do? We can multiply by 1. I know that there's 2.54 centimeters in 1 inch. Okay? And once again, 2.54 centimeters in 1 inch. And once again, 2.54 centimeters in 1 inch. Inch times inch times inch is inch cubed, so that crosses out with those three. And then so we're left with centimeter, centimeter, centimeter. So we're going to be left with centimeters cubed here. Make sense?
Yeah.
And then from here on out, it's just calculating the number. We have 1.84 times 2.54 times 2.54 times 2.54. Or should have just done that cubed. Make sure I didn't make any rough mistake. Okay. And we get 30.2 centimeters cubed. Or 30.2 cubic centimeters. So if you have this many cubic inches, you have that many cubic centimeters of water. Make sense?
Yeah.
Yeah.
Okay. So, next thing we need to talk about, maybe we have one more conversion factor. Oh, this is where we talk about significant figures. So first we'll talk about significant figures, then we'll do the example problem. Everything that we're talking about has to be measured in some way, right? And there's no such thing as a perfect measurement. I can't perfectly measure your height, right? And so there's something understood in how we write our measurements. There's just something understood that's being communicated in terms of how you write that measurement. So if I were to write that Peter is 1.7632 meters tall, if I measure him and I say he's that tall, and if I measure Jeremy and I say he's 1.8 meters tall, when we look at this numbers, when you see this number, you assume, just based on your intuition, you're already assuming that they must have been using something that is very delicate and can do very fine measurements if they were able to come up with this, right? Mm-hmm. Whereas this one, it looks like maybe I was just using a meter stick. Okay, here's what's understood in how you write out the measurement. In how you write out the measurement, it's understood that your last digit has a margin of error of 1 of that digit. So when I say that I think Jeremy is 1.8 meters tall, that is me saying that he's somewhere on the spectrum between 1.75 meters to 1.85 meters. He's somewhere there.
Yeah.
And so we round it to that.
Okay.
Why did you do square brackets on what? Right.
Include this, not include that, because I said we're going to round it. So if it's in this range, we write it that way. And then if it were in the range of 1.85 to 1.95, then we would have written 1.9 meters. Right? So when I write 1.8, the actual could have been something like 1.837, or it could have been something like 1.792. If Jeremy were exactly that tall or exactly that tall, and I was measuring with a measuring stick, in either case I would have spit out a number roughly, I would have spit out this number. You with me? Mm-hmm. So notice that our measurements kind of hide inaccuracies. They hide errors in our measurements. And there is an inherent error in that measurement. Now the problem with that is now when we multiply that number by something, our error gets bigger or smaller depending on the number we multiply by. But we could easily compound our error and make it worse and worse and worse and worse and worse, right? Mm-hmm. So when we talk about significant figures, that's how many digits we use to write it. How many significant figures? There's 2 significant figures here. And it's always understood that the last digit is within 1 of that digit in error. So there's a 0.1 error on this measurement. There's a 0.00001 error on this measurement. And that's implied in the way we write the number. Okay. Good? So now we have a problem. Let's say that we're trying to calculate the area of something. Okay? So I'm trying to calculate the area of something, some rectangle, we'll say. And let's say Peter has an amazing measuring device, and I am using a meter stick. With me? So Peter measures the width to be this. He gets a really precise measurement on it. And I measure the height to be this. And now we're trying to figure out the area. Okay. How should we write that area? Do we write that area as the product of these two numbers? So let me write that out really quick. 1.8 times 1.76382. Okay, so when you take the product of those, you get 3.17488 meters squared. So if I take your measurement and I multiply by my measurement, here's what comes out. Okay. You with me so far? Now imagine that we told someone, okay, here's our area. What do they assume when we tell them that this is our area? They assume that we measured it so precisely that this digit right here is within 0.00001 of what it should be.
But it's not.
But it's not. Not because Peter's measurement, but because my measurement was terrible, right? So here we had 2 significant figures. Here we had 1, 2, 3, 4, 5, 6 significant figures. When you multiply 2 numbers together, you have to use the significant figures of the smaller of the 2 numbers, the one with the least significant figures. So we cannot write this number this way. The only way we can write this number is we need to round to 2 significant figures, 3.2 meters squared. This is the correct way to write the area, not this.
Okay.
This accounts for the error that we had in our measurement. This doesn't. So this one's very misleading. This one's much better. Does that make sense? Mm-hmm. So when you're multiplying numbers together, then significant figures, you use the significant figures of the least one. You with me?
So is it significant?
So 2 significant figures. It's how many digits you need to write it out.
So what if it was positive? So what if that was like 18?
This still has 2 significant figures. Two significant figures.
Why is that one?
This also has 2 significant figures. Two significant figures. There's only 2 digits communicating the measurement. Here's why we call it significant figures. Because when you write it in scientific notation, you're going to have 2 digits multiplied by some factor of 10. So when I write this in scientific notation 3.2, that's 3.2 times 10 to the 0. When I write this in scientific notation, that's 3.2 times 10 to the, let's see now, we have 1, 2, 3, 4, 5, 6 zeros. When I write this one in scientific notation, that's 3.2 times 1, 2, 3, 4, 5, 6, 7 times 10 to the minus 7.
Do you include the 2 or just the zeros?
You don't include any trailing zeros or any leading zeros in counting your significant figures.
I mean for your exponent to the 10. Because you counted the 3 on the bottom one, but you didn't count the 2 on the
How many decimal places do we need to shift this 3.2 to make it look like this?
7.
We need to shift it 7 decimal places. So 1, 2, 3, 4, 5, 6, 7 decimal places.
Yeah, but you need
How
to
many
do
decimal
six.
places do we need to shift this one?
7.
Oh, 7. Oh, thank you. I just counted the zeros on this one. Oh, I made those symmetric. I didn't realize that. Yeah. 1, 2, 3, 4, 5, 6, 7. Thank you. Good catch. Good?
Yeah.
So that's how many significant figures. This has 2, this has 2, this has 2. Okay, trick question. How many significant figures does this have?
4.
4 significant figures. When the zero's in the middle, it matters.
Okay.
It's only leading zeros and trailing zeros that we can ignore. Make sense?
Yeah.
Okay, next thing. So when we multiply significant figures, you use the number of significant figures in the number with the least amount of significant figures. So we were multiplying a number that had 5 significant figures with the number that had 2 significant figures. Our product better only have 2 significant figures.
Oh, I see.
Use the least one. So when multiplying, use the least number of significant figures. That shows up in your measurements. When adding, it's another story. When adding, we use the least number of decimal places. So let's make sense out of this one really quick. So if I measure something to be 10.32 centimeters, some stick, we'll say Peter measures it. Peter measures out some stick and he measures it as 10.32 centimeters. And I measure some other stick and I say it's 1.1 centimeters. And we want to know what's the length when we lay both those sticks out. What's their combined length? What do we write? Do we write 11.42?
That makes sense.
No, we just write 11.4 because I have an error here that's not accounted for.
Okay.
So when you're adding, you use the least number of decimal places. This had 2 decimal places, this had 1 decimal place. We can only use 1 decimal place. When multiplying, use the least number of significant figures. When adding, use the least number of decimal places.
How about subtract and divide?
Subtracting is the same thing as addition. Division is the same thing as multiplication. What's division? It's multiplication by the multiplicative inverse.
Okay.
Okay, so that's significant figures. So now let's do a problem really quick with significant figures. All right, so we're going to use a little bit of relativity. No reason that you should understand this equation yet. Einstein's famous equation, E equals mc squared. What does this equation tell us? It tells us that the energy in a particle is equal to its mass, its rest mass. You don't know the difference between mass and rest mass, but technically it's rest mass. Anyways, the energy in a particle is equal to its mass times c. C is a constant which stands for the speed of light. So times the speed of light squared.
Okay.
You with me? Now we also know, first off, we have the speed of light measured very accurately. We have very accurate measurements of the speed of light. Here it is. The speed of light is 2.99792,458 times 10 to the 8 meters per second. We have measured the speed of light very accurately.
How do you measure the speed of light?
Shoot a photon over a really long distance. See how long it takes.
Okay.
There's better ways of doing it, but you can see in theory how to do it.
Yeah.
We're a long ways away from there. Anyways, so there's the speed of light. Now, the mass of an electron, that's something that's way harder to measure. The mass of an electron is roughly 9.11 times 10 to the minus 31 kilograms. Now, 10 to the minus 31, keep in mind how absurdly small of a number that is.
Yeah.
Okay. So an electron has this much mass. That is absolutely tiny. So you can see why it's insanely hard to measure the mass of an electron. And so we only can measure its mass to 3 significant figures.
Okay.
So now, our job is to try and find the energy in one electron. You with me?
Yeah.
So the energy in one electron is equal to the mass of that electron, just following the equation. So it's equal to the mass of that electron. What's the mass? That's 9.11 times 10 to the minus 31 kilograms. And now we need to multiply that by 2.9979248 times 10 to the 8 meters per second squared. Right?
Yeah.
Okay, so now we need our calculator. So 2.9979248. So we're going to, that doesn't work. So we'll do that times 10 to the power of 8, square that whole thing, and we'll multiply that by 9.11 times 10 to the negative 31. Okay, so now when I write my answer here, I'm looking on my calculator. My calculator shows 8.18766, and then it says E negative 14. What that means is times 10 to the negative 14. So that's what my calculator is telling me. What's the answer I should actually write here?
Just 8.18 times 10 to the...
8.19.
Oh, yeah.
Round it. 8.19 times 10 to the minus 14. We'll need 3 significant figures. Make sense?
Yeah.
And then, don't forget our
Units.
units. Sorry, just making sure I didn't make an obvious mistake. Okay, we're on the same page. Okay, so now our units. What are our units? Here we have kilograms. Here we have meters squared in the numerator and the second square in the denominator. So kilograms, meters squared per second squared. And that's the units of energy. Does that make any sense? No, shouldn't to you. That's fine. But those are the units of energy.
Okay.
We get tired of writing those units out there, so we have a shorthand and we call that a joule. 1 joule is 1 kilogram meter squared per second squared.
Yep.
And so we call it a joule to help us. So we have shorthands for writing some of these units so we don't have to write them all the time. But remember, it's always coming back to kilograms, meters, and seconds. Until we get to electricity and magnetism, then we'll introduce charge. Good? Okay, so converting units, we did that. We talked about significant figures. Think you're good with significant figures. And now we're ready to talk about vectors. Okay, and I told you I'm going to give you guys the big boy definition of vectors rather than the typical, a vector is just an arrow. Let's see if I can get that whiteboard good. Good enough. Getting a lot of glare. Maybe I always do. Okay. So, maybe motivated a little bit by jumping ahead. We need to get some actual good markers in here. Grab them from home. They're all dead from the break. Okay. Intuitively, here's how we use vectors in this class. A vector is just going to be an arrow. It's a direction and a magnitude, and we represent that with an arrow.
What does the magnitude mean?
Typically, we think about that as the length of a vector. So we can use real numbers to represent things. Like when I talk about the length of this room, I can just use a number to represent that. Or if I talk about the volume of this room, I can just use a number to represent that. We call those scalar quantities. If I talk about how long you've been alive, that's just a scalar quantity. If I talk about your mass, that's just a scalar quantity. I can just use one real number to represent that. You with me?
Yeah.
Okay, there's some quantities that we're interested in that we can't just use one real number to represent. For example, velocity. If I say this marker is moving at 10 meters per second, where is it going to be in a second? You don't know. Is it moving 10 meters per second that way? That way? That way? That way? All I did was give you its speed. I need to give you its velocity. I need to tell you both its speed and which direction that speed is pointed in.
Yeah. Okay.
So we can't just use one number to represent a velocity.
Yeah.
Make sense? We need to know both its direction and its magnitude. We need to know the speed and what direction that speed's in. So we use vectors rather than just one real number. We use a vector to represent a velocity. Similarly, we'll use vectors for forces. If I say an object experiences a force of 10 newtons, which way does it fall? Or which way does it move? Depends on which way the force is directing. There's a difference between me pushing you that way and me pushing you that way. So we use vectors to represent forces. So we use vectors to represent a lot of quantities in physics, and we use just real numbers to represent a lot of quantities in physics. If we just use a real number, we call it a scalar quantity. If we have to use a vector, we call it a vector quantity. So a velocity, we use a vector. Acceleration, we use a vector. Speed, we use a scalar. Length, we use a scalar. Making sense?
Mm-hmm.
Okay. So intuitively, that's what a vector does, is it gives you a direction and a magnitude. It's an arrow pointing in a direction is how we represent it geometrically. The length of the arrow is the magnitude, and then the direction the arrow is pointing is obviously the direction. Does that make sense?
So the magnitude is, well, the length, right?
The length.
Okay.
Length of the arrow will be its magnitude. Okay? So that's intuition for how we're going to talk about vectors. But a vector is not something with length and magnitude. That is not the proper definition of a vector. What's a vector? It's a member of a vector space. That's what a vector is.
Okay.
The same way, what's a real number? It's a member of the real numbers. If you want me to tell you what a real number is, it's something that satisfies all the axioms of the real numbers. That's what it is. What's a vector? It's something that satisfies the axioms of a vector space. It's a member of a vector space. A vector space has these axioms. So we are going to construct a vector space that satisfies these axioms that we'll use in this class to describe things like velocity, acceleration, forces, etc. You with me?
Yeah.
Okay. So we're going to define a vector space. And we're going to define a vector space, since we're mostly interested in two-dimensional problems like this, and then three-dimensional problems, we're going to define our vector space on R cross R for 2 dimensions and R cross R for 3 dimensions.
Okay.
Does that make sense what I'm saying? You good with R cross R?
That's the real numbers.
R is the real numbers. R cross R is all ordered pairs of real numbers. So that's the xy plane. And then R cross R gives you 3-dimensional space.
X,
XYZ, yes, the XYZ space. Make sense? So we're going to construct 2 vector spaces, one for talking about 2-dimensional space, one for talking about 3-dimensional space, and those will be the vector spaces that we're interested in this class. There's an infinite number of vector spaces that you could define. There's not just one vector space. What's a vector? A member of a vector space. So if you define a vector space, anything in a vector space is a vector. So now we're going to talk about what a vector space is, and then we're going to define a vector space that we want to use. That is going to satisfy these rules. With me?
Mm-hmm.
Okay, so let's go over the rules. A real vector space, meaning our vector space is going to be associated with the real numbers. A real vector space is a set, fancy V, along with two operations, an addition operation, which we'll represent with a circle plus in there, and a scalar multiplication, which we'll represent with a dot circle there,
Okay.
such that for any three vectors you choose, so this V is going to be the set of vectors, for any three vectors you choose, for all U, V, W, and V, in big V, for any three vectors, and for any two real numbers you choose, which is why it's called a real vector space, all these rules are satisfied.
Okay.
So what's a vector space? It's a set of things that we're going to ultimately call a set of vectors, and two operations, a plus operation and a times operation, such that all these rules are satisfied for any three vectors you choose and for any two real numbers you choose. You with me so far?
What's the difference between that addition and multiplication?
This is going to be a vector addition. We'll define this addition in our particular case over here.
And what is scalar multiplication?
We'll define the scalar multiplication that we're going to use over here. But whatever these operations are, it doesn't matter what they are, as long as they satisfy these rules, they're valid operations. And we have a valid vector space. Because you can define that addition any way you want, and you can define that multiplication any way you want, as long as it satisfies these rules, what you defined is a vector space. So there's an infinite number of vector spaces that you could possibly make up, and you could change it by changing what the V is. You could change it by picking different plus operations, and you could change it by picking different scalar multiplication operations. We're going to define two vector spaces for our purposes. And so we're going to define these in two cases. For the two-dimensional case and the three-dimensional case. That make sense? Okay. So, before we go through all the rules, let me just set up the vector space that we're interested in and define these operations really quick, and then we'll see all the rules. You with me?
Okay.
So our set V, we're going to start with the two-dimensional case. Our set V is going to be all the ordered pairs of real numbers. Sorry, I shouldn't have used alpha and beta there. All A, B, where A and B are real numbers. So all ordered pairs of real numbers. So 1, 7 is going to be one of our vectors. -2, pi is going to be one of our vectors, etc. You with me so far?
I think so.
You think so? Now, since when you represent two numbers, if I were to say, consider 1, 2 like that, you think I'm talking about the point 1, 2, not the vector 1, 2, right? Because that's how we represent points. So when we're talking about vectors, instead of using round brackets like that, we're going to use straight brackets like that. That's how we're going to signify we're talking about a vector rather than a point in this space.
Okay.
Just to jump ahead a little bit and give you a sense for what these look like, here's what the vector 1, 2 looks like geometrically. It goes in the x direction 1 and in the y direction 2.
Does it always start at the origin?
No. Here's the exact same vector. You can draw it anywhere you want. As long as it has the same magnitude and points in the same direction, it's the same vector. So here's a vector 1, 2, here's a vector 1, 2.
How do you know which direction it's pointing on?
Pointing that way. These two vectors are pointing in the same direction, they're parallel.
No, I'm saying you write 1, 2. I'm saying.
Oh, you can figure it out. We'll see how to figure it out from basic trig.
Okay.
So it's saying that doesn't matter what numbers you put in them. The first one, which would be where the x coordinate is just.
This is how far the arrow goes in the x direction, here's how far it goes in the y direction.
So it's like
I can draw it without any coordinate system like that. Here, let me draw it one more time. Try it here. Goes over 1, up 2.
It's just like the slope.
Sure.
Okay.
You see how you could easily get the slope from that. What's the slope of that? 2. Correct. And the slope obviously gives you the direction.
Yeah.
And then you could use the Pythagorean Theorem to get the length. Correct. So anyways, here's what our vectors are going to look like, just to give you some intuition on the things we're defining. You with me? But they're vectors, not points. right? The point 1, 2 is just that. This is the vector 1, 2, this is also the vector 1, 2, this is also the vector 1, 2.
But it keeps going past 1, 2.
No, this is the end of it, right there.
That's
the whole vector.
Then why do you draw the arrow?
Because direction matters. There's a difference between that vector and this vector. This vector says you're moving that way. This vector says you're moving that way.
So would the vector 2, 1 be going that way?
So this vector right here is a vector negative 1, negative 2. It goes back 1 and down 2.
And then stops.
And then stops. Yeah, it's this whole thing. That's the end of it. Starts and ends there. That arrow doesn't mean going off to infinity.
How about the vector 2, 1?
The vector 2 to 1, that would look like this. 2, 1. Typically we draw them at the origin because that's easiest, but they don't have to be at the origin. You can put them anywhere you want.
Okay, I see.
Good? So that's geometrically roughly what we're constructing over here, abstractly. So our V is going to be R cross R. It's going to be order pairs of real numbers, like this. Anything like this where alpha and beta, let's not use alpha and beta since we used them for specific things over there, let's call it A and B. A and B, where A and B are real numbers. So pick any possible 2 real numbers you want, stick them in brackets like that, that's inside our V that we're talking about.
Okay.
With me so far? How many things are in V? Infinite. Okay. Just quick sanity checks, making sure we're on the same page. All right. So now let's define this addition operation. How are we going to define this addition operation in our case? We're going to say that if you have 2 vectors, so let U be the vector A1, A2, and V be the vector B1, B2. With me so far?
Yeah.
So we have those 2 members of that set, these 2 vectors. We're going to define vector addition so that it's this. So this is A1, A2, and this is B1, B2. We're going to define U plus V so that it's A1 plus B1 and A2 plus B2. Now, since A1 is what? What is A1?
It's you.
It's just a real number, right?
Yeah.
And B1 is just a real number, right? So this addition right here is just the addition on the real numbers. So that's normal. This is just normal addition like you're used to. So using our definition of addition now, if I take this vector and I add it with this vector, then that is equal to this vector. You with me?
Yeah.
Pretty straightforward, right? Okay. Now, the other operation that we need to find is this scalar multiplication. That's when you take a vector and you multiply it by a scalar, or you take a vector and you multiply it by a real number.
Okay.
So C here is a real number. It's not a vector. U is a vector, C is a real number.
So you can't multiply 2 vectors together?
We will define an operation to multiply vectors together. We have 2 different ways of doing it. But that is not what this is talking about. This is not multiplying 2 vectors together. This is multiplying a vector by a scalar.
The scalar is basically like a constant on the
A real number.
Okay.
Just a real number. Technically, it could be a complex number, which is why we say that. In this case, we only care about real numbers. That's why we say scalar.
I see.
All right. Anyways, so C here is just a real number, but U is actually a vector. So what do we get when we perform this operation? So remember, U is A1, A2. So C, scalar multiplication U, is the same thing as C times A1, C times A2. So if you see 2 dot 3 negative 9, then that is equal to the vector 6 negative 18. We doubled it. Geometrically, what does that look like? That's taking a vector and making it twice as long. You doubled it.
Yeah, that makes sense.
Similarly, if that would have been a 1/2, then this would turn into 3/2. This would turn into negative 9/2. And that would be squishing that vector down to half its size. So you either scale it up or you scale it down. So scalar multiplication. Change the scale of the vector.
How does the adding look?
Huh?
How does adding change the vector?
What does it look like to add two vectors together? That looks roughly like this. So go back to what I initially had here. Here's vector A, 1, 2. Here's vector B, 2, 1. Now when we add those together, we should get the vector 3, 3, right?
Yeah.
Which is this vector 3, 3. So C, we're going to say is B plus A. Geometrically, the way that you can add vectors together is you take the tail of one vector, that's the side, the tail end is this end. You take the tail of one vector and stick it at the head of the other vector.
Okay.
And where they end up is where is what vector addition gives you. So if I took that arrow and stuck it right there, that's that right there, then that ends up where their addition ends up. Which makes sense, right? B took us 2 and 1. A took us 1 and 2.
Can they cross? Can vectors cross?
They can cross. The point is, if you're adding vectors together, geometrically what that means is you're taking that and you're sticking it there.
Okay.
That's just a geometric interpretation of addition. Make sense? Okay. So we've got our vectors. Here's how we add them. Here's how we multiply them by a scalar. And now we can check to see that they satisfy all these rules, and all these rules are going to be satisfied with our vectors.
Okay.
So check them really quick. For any two vectors, if I add them together, is it still a vector?
Yeah, because it's still in the real numbers.
Yes, because a real number plus a real number, notice that when we add them together, we just add their components, their real numbers. A real number plus a real number is always a real number. A real number plus a real number is always a real number. And so you have real number, comma, real number. And anything that's a real number, comma, real number is one of our vectors. So it is true that a vector plus a vector always gives us a vector. We satisfied that condition. Okay, next condition. Is it true that u plus v is always equal to v plus u?
Yep.
Is it commutative? Yes, because notice how we defined it. A1 plus B1 is the same thing as B1 plus A1. So since addition on the real numbers is commutative, then addition on our vectors is commutative. Make sense? And then finally one more. Last one. U plus V plus W. If we add these two vectors together first, and then we add U, that's the same as adding U and V first, and then adding W. Is that true? Yes. Once again, since addition on the real numbers is associative, then we know addition with our vectors is going to be associative. Does that make sense?
Yeah.
Okay, next one. Does there exist some zero vector? This isn't the zero number, this is the zero vector. Does there exist some zero vector such that u plus that zero vector always gives me u?
It's a zero vector.
Yeah, that's just a vector 0, 0. We have that. Notice that with this vector, you can add that to any vector you want, and you still get the same vector back, right?
Would that just be a point, or would that just not be on a correct geometric?
Geometrically, yeah, we don't have a good way of representing that geometrically. That's the one exception to our geometric representations. So yeah, you can represent it as a point if you want. A vector with no magnitude. Okay, next thing to check. For every vector in our vector space, does there exist some other vector, we'll call it the negative of that vector, such that their sum always gives us 0?
Yeah.
Yes. So if u is equal to a1, a2, then negative u would be the vector negative a1, comma, negative a2. Right? And now if I add this vector with this vector, that would give us the 0 vector. So it is the case that for any vector you have, it has an opposite vector. Geometrically, what does that mean? It means for any vector you have pointing that way, we can always flip the directions and point it in the opposite direction. And if I take that vector and I add it with that vector, that gets us back where we started, just that point. Make sense?
Mm-hmm.
Okay.
Is the 0 that gives you the vector 0?
Yeah, it gives you the vector 0. So notice, if we did u plus negative u, that would be equal to a1 plus negative a1, comma, a2 plus negative a2, right?
Yeah.
Which is equal to 0, 0. So it gives us the 0 vector, not the number 0. But those two behave very similarly. Okay, so we took that, we took that. Okay, is it true that for any vector, if we scale it, it's still a vector?
Yeah.
Yeah, because the way we define our scaling is that's just taking a real number and multiplying it by a real number. And a real number times a real number is still a real number, always and forever. And so it's still just two real numbers, therefore it's still a vector. So that's still a vector. Okay, now we need to check this property. If I take two vectors and add them together and then scale them by some quantity alpha, is that the same thing as scaling it by alpha first and then adding them together?
Should be.
Should be. Let's just check it really quick. So we have,
Sorry, not borrowing your key. Yeah.
so let's check it real quick. We'll start out here. So we have alpha scaling up u plus v, right?
Yeah.
Scaling up u plus v. Well, that's equal to alpha scaling up u plus v is just the vector a1 plus b1, comma, a2 plus b2. Right? Now if I scale it up by alpha, that gives me the vector alpha times a1 plus b1, comma, alpha times a2 plus b2. And my vector, right?
Mm-hmm.
Now, inside of here, we're just always talking about real numbers and the plus and multiplication on real numbers, right?
Yeah.
Inside of there. So I can rewrite this as, this is the same thing as I can distribute the alpha into that. So I can say that's the same thing as alpha times a1 plus alpha times b1, comma, alpha times a2 plus alpha times b2. You with me?
Yeah.
And notice now, that's the same thing as alpha times u plus alpha times v. Does that make sense? Okay, so we just barely showed that this property holds. Good? Okay, now we need to show that this property holds. Now this one can be a bit misleading because sometimes we're talking about scalar multiplication and sometimes we're talking about real number multiplication. Important to keep that distinction in your mind. So it says, if we take a vector and we scale it by b, first off, if I take a vector and scale it by b, I'm left with a vector, not a real number, right?
Yeah.
So this is still a vector. So then if I take that resulting vector and scale it by alpha, that's the same thing as just starting out by taking these two real numbers and multiplying them together, alpha times beta, and then scaling our vector by that product.
That makes sense.
That makes sense, that's good, and you understand why that's circle dot, and that was just regular multiplication, right?
Because those ones are.
That's the important distinction here. And then, yeah, we could check this easy enough. So when we multiply this one out, we take the components of u, we multiply them by beta, and then we take those components and we multiply them by alpha. So when we multiply that one out, we obviously get alpha times beta times A1, comma, alpha times beta times A2. Right? For this side?
Yeah.
And then obviously that's the same thing as this.
Okay.
Clear how those are the same? Cool. Another one. If we add the two real numbers together and then scale our vector by their sum, that is the same as adding the two vectors together scaled by alpha and beta.
Can you write that one out?
Yes, we absolutely can. So let's do alpha plus beta scaling u. So for this side, that's going to be, that vector is going to look like this. That's going to be alpha plus beta times A1, comma, alpha plus beta times A2. That's what this is. Oops, sorry, that's what this is, right? We scaled u by alpha plus beta. I took that component, multiplied by alpha plus beta. I took that component, multiplied by alpha plus beta. Good?
Yeah.
Yeah.
And now in here it's just real numbers, so just do some distribution. This is the same thing as alpha times A1 plus beta times A1, comma, alpha times A2 plus beta times A2, right? Just distributing the A1 into that and just distributing the A2 into that. Good? Okay. And then that's the same thing as alpha circle dot A1 A2 plus vector plus beta scale dot A1 comma A2.
Yep.
Good? So you see how those are the same? Finally, the last rule. Now this 0 up here, this was a 0 in the vectors. The 1 here is regular 1, real number 1. So when I take u and I scale it by 1, I better just get u.
Yep.
Which is obviously obvious. If I take A1 and A2 and I multiply those by 1, I'm left with A1, A2. Okay. So we have a vector space. And the elements of a vector space we call vectors. That's exactly what a vector space is.
Okay.
And so we just proved that the things we're calling vectors are in fact vectors. You with me?
Yeah.
Now so far we've just been talking about vector space for handling the two-dimensional case. We also have a vector space for the three-dimensional case. So I could also have, in the three-dimensional case, my vectors are going to look like, U is going to look like A1, A2, A3. And B is going to look like B1, B2, B3. And we still define addition and scalar multiplication the same way. U plus V, we define to be the vector A1 plus B1, comma, A2 plus B2, comma, A3 plus B3 plus B3. And scalar multiplication works the same way. So we define for the three-dimensional case exactly the same way that we did for the two-dimensional case. It just adds one more component to all our vectors, and all these things still hold using the exact same logic. And we don't need to validate that one, right? Mm-hmm. Do you understand what I'm saying? Okay. So those are the only two vector spaces that we use for the two-dimensional case and the three-dimensional case. Two-dimensional vectors, we use two components to represent. Three-dimensional vectors, we use three components to represent. When we represent them geometrically, the first component represents how far you go in the x direction, the second component represents how far you go in the y direction, and if it was a three-dimensional one, the third component represents how far you go in the z dimension. All that make perfect sense?
Yep.
So how are there infinite vector spaces?
I can make vector spaces where the members of vectors are polynomials.
What's that?
Okay. there's an infinite number of vectors. Let me give you a trivial vector space. One example of a vector space we could use, for example, well, first off, here's how there's infinite. I could also just do a 4-dimensional vector space, and a 5-dimensional vector space, and a 6-dimensional vector space, doing it the exact same way we've been doing. Or a 1-dimensional vector space. Notice that with the way that we defined it, a 1-dimensional vector space and just a real number act the exact same. No difference between them. I could also do the vector space where it just contains the 0 vector. I could have B equal to the set where we just have a 0 vector in there. That's a trivial vector space. And that satisfies all those axioms. Is it true that for any two members in there, when you add together, it's in there? Is 0 plus 0 0?
Yeah.
Yep. Is it true that 0 plus 0 is the same thing as 0 plus 0? Yep. Is it true that 0 plus 0 is the same thing as 0 plus 0 plus 0? Yep. Is there a 0 in there? Yep. When you scale 0 by any real number, is it still in there? Yep. And we don't just have to work with real numbers like this. You can create vector spaces on lots of things that there's no reason it should appeal to your intuition right now. So, yes, these are like the two easiest cases of vector spaces that we typically work with. Two most intuitive ones. But there's tons of different types of vector spaces. Okay. So, geometric interpretation of vectors, I think we've already got a good feel for that one.
Why is there an arrow above the A? Is that
Oh, thank you. Thank you for saying that, because 2 points now, before we move past this. Now, I used a circle with a plus here and a circle with a dot here to try and make clear that these are different operations than what we're talking about on the real numbers. From here on out, we will drop that notation. When I'm adding vectors together, instead what we do is we put an arrow above our variable when it represents a vector. So when I want my variable to represent a real number, I just use a variable like you. If I want my variable to represent a vector, I put an arrow above it, like that. So that means we're talking about a vector.
Does it matter which way the arrow goes?
No, but we'll always draw it that way.
Okay.
We're just saying this variable represents a vector. And so for vector addition, you'll see something like this. U plus V. And you'll never see that circle plus again. That's just something I made up to help explain what was going on.
Okay.
Furthermore, when we do multiplication by a scalar, you won't see a circle dot, you won't even see a dot. We'll just do 3u plus v. And that means scale u up by 3. Okay? Because later in this class, we're going to define what it means when you see something like this. And I don't want you to get confused. That's an operation we haven't defined yet. We're going to define what we call a dot product.
Okay.
It's not multiplication.
It's a type of multiplication. It's not multiplication on the real numbers because those aren't real numbers. It's an operation that we need to define. And we'll define it.
So if you
Because we're going to have two different types of multiplications. We're going to have one that looks like that, and we're going to have one that looks like that, and they're going to be very different things. And we'll define exactly what they mean.
Two different. Okay. Okay.
that's an X.
Look, it's a multiplication operation the same way that we can think about AND as a multiplication on Booleans and OR as an addition of Booleans.
Yeah.
We don't need to just focus on the plus and the times of just what goes on with the real numbers.
Okay.
That's the plus on the real numbers and the multiplication on the real numbers. There's lots of plus and multiplication operations. And so we already defined a plus operation, which happened to use addition on the real numbers. And now we'll define a multiplication between two vectors that we'll define two different ones that are useful.
You're multiplying two vectors together, you just draw them next to each other, is what I'm saying?
There's two different ways that we multiply vectors together. We have what we call the dot product, and we have what we call the cross product.
Which one is the circle dot?
This was scalar multiplication. That wasn't between two vectors. This is a real number, that's a vector.
Oh, we didn't even multiply vector by vector.
We never did vector by vector multiplication.
Okay.
Good point. Make sure that's clear. We did vector by vector addition, And then we did vector by scalar multiplication, but we have not done vector by vector multiplication. Good. So, glad you brought that up. So from here on out, we will not use that plus anymore for vector addition. We'll just put a plus there. And you're expected to infer from context, so we're talking about vector addition. And we will not use a circle dot to represent scaling a vector. We'll just stick the number right next to it. And you're expected to infer from context, we're scaling a vector.
Okay.
And you'll catch on pretty quick. It'll be pretty obvious from context what we're doing.
Yeah.
Okay. So here's how we'll represent vectors now. Letters with arrows above them. There's a vector, there's a vector, there's a vector. Here's the geometric representation of that vector. Here's the geometric representation of that vector. Here's the geometric representation of that vector. Now, since addition is commutative, we didn't have to do B and then A. We could have also first done A and then B, like that. And either way gives us C. So here's vector A right there. Here's vector B right here. And those give us vector C either way.
Yeah.
Good?
Mm-hmm.
So some people call this like the parallelogram law or something like that, because if you create a parallelogram with the two vectors you're adding together, the resultant vector cuts the parallelogram in half. Good? Mm-hmm. Okay. Now we're going to talk about the magnitude or the length of a vector. Now, obviously, we know how to get the magnitude or length of this vector. What's the length of this vector?
2.
Now, it goes over 1 and up 2. What's the length of the vector? Put a dotted line here. That's a 2. That's a 1. Okay, what's the length of the vector?
3.
Oh my goodness. Let me go back and give you a 0 in calculus. Okay, this is a right angle.
Oh, it's a hypotenuse,
So what is it?
it's 2 squared plus 1 squared, so 5
No.
squared.
It's the root of 5.
Square root of 5. Holy cow, that is painful, you guys. You should not be struggling that hard with the Pythagorean Theorem. For any right triangle, if that's A, that's B, that's C, A squared plus B squared equals C squared. So 5 is equal to C squared, so C is equal to 5. No, square root of 5. Good?
Yeah.
Don't make me reprove the Pythagorean Theorem. Is that what we need to do? Go back to basics?
No.
Go back to first aid calculus? Okay, Pythagorean Theorem. All my lap. Okay, so what did you do? You took that squared plus that squared under the radical. In general, pretend now this is just a general vector. We don't know exactly what its components are. All we know is that that distance right there, whatever it is, we're just going to call it A1. You with me?
Mm-hmm.
And that right there we're just going to call A2. So this is now just a vector A1, A2. And it's just pointing in some direction. Don't pretend you know anything about which way it's pointing. Then what is the length of that vector?
A1 squared plus A2 squared rooted.
Under the radical. Perfect. So the magnitude of A, which we represent like that, we put absolute value signs around it. That represents its length or its magnitude. Is equal to the square root of A1 squared plus A2 squared.
Is that just representing the magnitude, or does it change the number?
This is a symbol for the length of that vector. Now, because that is a lot to write the length of the vector, and we're super lazy and we don't want to do that all the time, sometimes we'll just instead call that A. So A arrow means we're talking about the vector. A by itself means we're just talking about the vector's length, because we make reference to the vector's length a lot, right? You can imagine if you're talking about velocity, you're often going to make reference to its speed. So A arrow, if that's a vector, just A by itself represents its magnitude or its length. guess we have that right here. So if u arrow is equal to a1 comma a2, then the magnitude of u arrow is the square root of a1 squared plus a2 squared. And then u is the same thing as the magnitude of u arrow.
Yeah.
Same thing I just said, right?
Yep.
More notation. Another way we conveniently talk about these things. So if a1 is represented as a vector, if the vector a is represented as a1, a2, you with me so far?
Yeah.
Then we also have this notation. If I write a sub x, that means the x component of the vector. Or in other words, a1. And if I write a sub y, that means the y component of the vector.
And if it's 3 dimension, it'd be AZ.
And if it's 3 dimensions, it'd be AZ. Exactly.
Okay.
Good? So now some basic trig about these vectors. So here's my vector A right here. You with me? Mm-hmm. The hypotenuse then of that vector, the length of vector, we represent with just A.
Okay.
Its distance in the x direction, or its x component, we represent with AX. And its distance in the y direction, or its y component, we represent with AY. Now, the natural thing that you're going to want to do with a lot of vectors is figure out the angle that they're pointing at.
Okay.
Make sense?
Mm-hmm.
So, we're often going to need to find that theta, or work with that theta, the angle that it's pointing at. So, going back to some of our basic trig identities, I know that the sine of that angle gives me the y over the hypotenuse.
Yeah.
So sine of theta equals ay over a. Similarly, cosine of theta gives me ax over a.
Okay.
And tangent gives me the slope, or gives me ay over ax. And then cosecant is just a reciprocal of sine, secant is just a reciprocal of cosine, cotangent is just a reciprocal of tangent. So you'll be doing basic trig with these vectors a lot.
This where it's going to ask us to find angles and whatnot?
Yeah, we'll do an example problem right now with some of this.
Okay.
Let me find what page we're on in the book. By the way, this is the actual textbook. Look how thick that thing is.
That's fast.
And that's only 2 semesters worth of physics. So we're going to go through half this.
Wow.
Ease. Okay. So, I have it set up a little bit over here. Move the camera. Alright, so let's read that first problem. What's it after? Oh, that one didn't have much of a story. That's the other one that has a story problem. So let's just look at it. So my job is to find the x and y components of the vector d. Here's the vector d.
Okay.
I'm supposed to find the x and y components of this vector. Given that alpha, the angle, is 45 degrees, and d, or the magnitude of our vector, is 3 meters. So now I need to find the x and y components of this vector. You with me? Mm-hmm. So, let me draw a picture over here really quick of our vector. Here's our vector. I know that this right here is 3.00, by the way. So the fact that they did 0.00 like that specifies we know it to 3 significant figures. That's why they put those zeros there.
Okay.
And that's what the number actually came out as. Because if it was only 1 significant figure, no one would put those zeros there. So we're saying we measured extra carefully and those next 2 numbers were in fact 0. Make sense? Mm-hmm. Okay. So here's our vector. And we know that this angle right here is 45 degrees. Right?
Yeah.
So I need to find this, and I need to find this. How do I find this length right here?
Just the
cosine. Perfect. So it's just 3 times cosine of 45 degrees. Right?
Yeah.
And this one right here is
Sine.
3 times sine of 45 degrees. And so this one is going to come out to, what's the cosine of 45 degrees?
1.
It's
Root
root
of
2 over 2.
Root 2 over 2. Meters. So then we need to get out our calculator. And actually calculate what that is, because you need good numbers. So, really quick, 3 times the square root of 2, whoa, 3 times root 2 divided by 2 is equal to, so here's what's on my calculator when I put this in. I get 2.12132. Question. So now let's actually write the x component. So I'm going to say that d sub x is equal to, what should I actually write here now?
2.12.
Give you one more guess. That's wrong.
It's 3 significant figures. And you round down. You're saying that only has 2 significant figures?
No, the x is positive, the y is negative.
No.
So what,
45
choose
degrees is
2.1?
only 2 significant
Yeah.
figures. That does not say 45.0 degrees.
What?
It was just 45 degrees. The angle was only known to 2 significant figures.
Yeah.
It was at 45.0. It was just 45 degrees. So 2 significant figures, 3 significant figures. Square root of 2 we know to as many significant figures as you want. Don't worry about that one. But so our answer here is just 2.1 meters.
Okay.
Alright. And what's my dy?
That would be negative 2.1.
Negative 2.1 meters. Direction matters. Perfect.
Okay.
Good? Don't forget those tricky angles.
Yeah.
Those have significant figures too. Don't pretend angles aren't as significant as lengths.
How do angles fit in with physics units? Like, if it's
An angle is something you measure, just like anything else. You use a protractor to measure an angle.
So it'd be length.
Oh, angles are dimensionless. I guess you could talk about degrees as a unit, but radians, we don't talk about radians as having a unit.
So how does that fit into physics?
So you could talk about a degree as a unit if you want. That works. A degree is a unit. Okay. Let's see, next thing we're going to be talking about. Did that. I think we can just go to the next problem before we talk about unit vectors. Okay, so let's do this next problem. Can you erase her? The next problem there. So here's what's happening. You are a part of a game show. You're competing with a bunch of contestants. And you're out in a cornfield or something to that effect. And there's a key to a Porsche buried somewhere in that cornfield. First person to dig up the key gets the Porsche. You're competing with some other people. And so you are given these directions. The person tells you, if you go 72.4 meters, 32 degrees east of north, and then you go 57.3 meters, 36 degrees south of west, and then you go 17.8 meters due south, you'll end up where the key's buried.
Okay.
And so your job is to try and figure this out. And I think the point that the author is going to try and stress here is to do all the addition first and then do the calculation. So remember how we define addition. It's just adding up the exponents and then adding up the y components and then adding up the z components. Okay? So he says, you being smart, rather than taking your meter stick and your compass and marching off in the A direction and then in the B direction and the C direction, so instead of you doing some sort of, I don't know what the picture's going to look like, something like that, following these three vectors, instead you're going to be smart, you're just going to calculate the resulting vector and walk straight there. So you're not going to do A, and then B, and then C. You're just going to go, add them up real quick, and then go straight for the key. You're smart. So next time you're on that game show,
I'll remember that.
this time you're going to win. Not be one of those fools.
Gotta get that folder.
All right. So that's what we're going to do. Anyways, so let's figure out all the various components. This is only in 2 dimensions, so we just have x and y components. So ax, really quick, what's that going to be equal to?
72.4.
Let's get a picture of this thing.
That's the hypotenuse.
So we've going 72.4 degrees, 32 degrees east of north. So if we draw this up, typically we let north be this way, right?
Yeah.
North, east, south, west. We're going 72.4, 32 degrees north of east. So here it is, here's our 72.4. This right here is what's 32 degrees, right?
Oh. Missing.
Good? So what's AX?
It's cosine.
It's cosine. So 72.4 times cosine of 32 degrees.
So if we brought a calculator to the game show.
Oh yeah, you get a calculator. Obviously it's a game show. And then AY is equal to,
Same thing as sine.
same thing but sine, perfect. So that's for our A vector. For our B vector, Bx is going to be equal to, this one is 36 degrees south of west. So this one looks like this, where this is 36 degrees. Here's west, it's 36 degrees south of west, right?
Yeah.
So this one, what's our x component going to be?
It's just gonna be the cosine.
We're going to use a cosine. And what was our magnitude? 57.3. And that one's 36 degrees. Sine 36 degrees. And then finally, our last one, our last vector is 17.8 meters due south. So it's pointing straight down. So what's Cx equal to?
0.
0.
0. And Cy?
17.8.
Well, negative 17.8 now. Now we can just plug it in, right?
Yeah.
Negative 17.8, and obviously meters on all these. Meters, 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 meters.
So don't you want to negative at the y and the x?
Yeah, we should pay attention to signs as we were doing this, huh?
It's just-
So really quick, AX and AY, those ones are both positive, right?
Yeah.
Because we're talking about east of north. This one we're talking about south of west, so they're both negative. Right? Because it's in the third quadrant. Okay, and then 0, negative. Perfect. So now we can figure out our resultant vector. We just add up all the x components to get our x component, and we just add up all the y components to get our y component, right? So our x component, that's going to be 72.4 times cosine. Let me make sure I'm in degrees. Degrees, okay. So 72.4 cosine of 32 degrees plus, or minus I guess, minus 57.3 times cosine of 36 degrees, and then plus 0 for that last one. And when I have it on my calculator says that comes out to 15.042 for our x.
Wouldn't it just be 15?
Which isn't what they got. So let's double check, make sure I plugged in all my numbers right. Oh, oops. I think we did this one wrong. I think we said it right, but I just wrote it wrong. It's supposed to be sine and cosine, right? This one's flipped.
Yeah, why is that?
I thought we said it right. Sorry. Here's A. Right? And here's our angle, 36.
Oh, that's right.
It's the sine.
Opposite over by this silver toe.
This side right here, if we call this side A, this side right here is A sine of theta.
Oh, yeah.
And this is a cosine. I think we even said that when we were doing it, and I just wrote it wrong. Okay, there we go. So that's why I plugged in wrong. Come back here. Put in sine, not cosine. Now we get negative. Yeah. Goes back some. So roughly what the picture looks like is something like this. Roughly. Anyways, so I got what should we call the resultant vector? Should we just call R? So R sub x is equal to negative 7.99052 meters. And we'll think about significant figures here in a second. The Ry then is going to be equal to, and we can plug it into our calculator, but since we got the x right now, I'm pretty sure we get the y right, so I'll just steal his answer. Oh, he already rounds. Oh, he's so easy. You'll get 9.92 meters. Okay.
Are you supposed to do 3 digits?
We should have 3 significant figures. No, we should only have 2 significant figures.
Yeah.
So he just wrote 3 significant figures there, but then when we say how we actually move, we'll do 2 significant figures.
Okay.
So no, we left it at 3 significant figures. Okay, that's because I wrote this wrong. He wrote 0.0 on all the degrees. So everything has 3 significant figures. I wrote it wrong.
Okay.
Okay, so anyways, so everything does have 3 significant figures. So we need to figure out, now not just the components. I mean, we could tell you, okay, go negative 7.99 meters this way, and then 9.92 meters this way. But it'd be faster if you could just walk directly there, right? So let's instead find the angle that you should walk at, and let's find the distance you should walk. So we'll find this angle maybe. We'll make this the angle we find. I don't know if that's what the author does. But we'll find that angle, and then we'll find this distance. You with me? So I know that tangent of that angle, tangent of theta, is going to be equal to what? Rise over run.
So sine.
How high do we go?
9.92 over.
9.92.
Negative.
over, no, because we're doing this angle, not this angle. We're trying to figure out what that angle is.
Yeah.
So redraw our picture. We can redraw our picture like this. If we measure that angle from where we should start measuring angles, it looks like this. Okay. So now everything's positive.
So what? It's just 9.92 over 7.99?
Over 7.99.
Okay.
So that's what the tangent of this angle is, if we're talking about that angle. You notice that we started measuring this angle from right here. Okay. So, then theta is equal to what? How do you get it? I know you don't know the number, but how do you calculate it?
Just divide the two numbers.
It's equal to the arc tangent of 9.92 over 7.99. The inverse function.
Yeah.
Tangent takes an angle and spits out a slope. Inverse tangent takes in a slope and spits out an angle. So you have an arc tangent on your calculator, and so you'll plug that into the arc tangent, and you'll get it. So we'll do the arc tangent of 9.92 divided by 7.99, and we get 51.2 degrees. So theta is equal to 51.2 degrees. And now r, the distance you should travel, is equal to what? How do we get that one?
Pythagorean Theorem.
Pythagorean Theorem. We're going to do the square root of rx squared plus ry squared, right? Mm-hmm. Okay, so when we plug that into our calculator, what do we get? So we're going to do, notice that when you square a negative number, it becomes positive, so I don't need to worry about squaring a negative. I can just square the positive, right? Okay. So I do 7.99 squared plus 9.92 squared, all under the radical, and we get 12.7. So you want to walk 12.7 meters north of west, or 12.7 meters, 51.2 degrees north of west. And you'll find the key into it. Hooray. Okay, definition. You'll see these symbols a lot. I hat. Now, it's not I with an arrow over it for some reason. It's just I with a hat over it. A little bracket we call I hat. I hat. This is special notation for the vector that points one unit in the x direction.
Okay.
J hat is special notation for the vector that points one unit in the y direction. Okay. If we were in 3 dimensions rather than 2 dimensions, I hat would be the vector 1, 0, 0. 1 unit in the x direction. J hat would be the vector 0, 1, 0, 1 unit in the y direction. And then we say k hat for 1 unit in the z direction. So just to make sure this is abundantly clear, here's my xy axis, xyz axis. Trying to draw 3 dimensions. This is x, this is y, this is z. I hat is a vector right here. This is I hat. And it goes 1 unit in that direction. J hat would be the vector right here. And it goes 1 unit in the y direction. And k hat would be the vector right here. And it goes 1 unit in the z direction. You with me?
Yeah.
Okay. So, another way that we can represent these vectors. You know that I can take the vector A and I can represent it as its x component, comma, its y component in brackets. That's one way I can represent it, right? Mm-hmm. I can represent it with an arrow. That's geometrically one way I can represent it, right? Another way I can represent it is A hat, AX, the x component, times I hat, plus the y component times J hat.
Why do we care about doing it that way?
Because notice that this is all an expression that you're used to working with, whereas this isn't really an expression. So now it's completely an algebraic expression.
Okay.
How is it equal to adding them together?
Yeah, so let's draw a picture really quick of this in the two-dimensional case. So let's draw some vector A. Here's vector A. And let's pretend that A is equal to the vector. What does that look like roughly?
3, 5.
Something like 13, 7. Right?
Mm-hmm.
So there's A hat. Here's I hat. And here's J hat. Right?
Yep.
Now what we're saying is the vector A is also equal to 13 I hats plus 7 J hats. So imagine I took 13 I hats. Where does that end up? That takes me 13 units this way. So that's going to take me right there. So if I take 13 I hats, etc., that gets me right here. And if I add on top of that 7 J hats, then that's going to get me right there.
Okay.
How do you show that that's a vector? Is it still a vector?
Oh, it's actually calculated then. I see what you're saying. Okay, so it's clear that this is a vector, right? Obviously. So let's actually do this calculation using the operations we defined. So 13 I hat is the same thing as 13, and we're scaling up the vector 1, 0, plus 7, scaling up the vector 0, 1. Just plugging in I hat and J hat, right? Which is equal to and then using vector addition, 13 plus 0 is just 13, 0 plus 7 is just 7.
Yeah.
Which is 8. So I hat is the unit vector in the x direction. So we go 13 units in the x direction and 7 units in the y direction. 13 units in the x direction, 7 units in the y direction.
I see.
Same thing, right?
Yeah.
Once it clicks, it's pretty straightforward, but it might take a second for it to click. So useful vectors that we often make reference to: I hat, J hat, and K hat. Okay, so now we're ready to define our two multiplications, our two vector multiplications. The first vector multiplication we're going to define is called the dot product. So when you see a dot between two vectors, it's talking about the dot product. When I have two vectors, A and B, so if I do A dotted with the vector B, by definition, that we're going to use in this class, that is the magnitude of A times the magnitude of B times the cosine of the angle between them. By definition.
Okay.
Now, geometrically, what does this do? So geometrically, what this does, if I have A here and B here, here's A, here's B, here's the angle between them, theta, right?
Yeah.
Geometrically, what this does is it projects A onto B. That's the first thing it does. And then scales it up by the length of B. So let's take this one step at a time. So this right here is B, the vector B. Really quick, if I take A and I project it onto B, so imagine I put a light source directly above A and we looked at its shadow on B. Then that's going to be this vector right here, right? Mm-hmm. What is that? What is this length right here?
AX.
AX, or A, if we were to calculate it, it'd be A times cosine of theta, right?
Yeah.
You with me so far?
Yeah.
So now imagine for a second that B had length 2. You with me? So we project it onto B. Maybe B goes longer. Make sure that we're not confused by those lining directly up. B's however big B is. It could have also been smaller than A. It could have been just that big. Or it could be really big. So first off, here's A projected onto B, right? Here's a component of A in B's direction. And then we scale it by B. So if B were 2, we would make it now twice as big. If B were 1/2, we make it 1/2 its size. So we scale it by however big B is, by the length of B.
Okay, that makes sense.
So that's what we're doing here. AB cosine of theta. And notice that that's the exact same thing as taking B and projecting it onto A, because then that would give you B cosine of theta, and then scaling by A. So you can think about it as projecting A onto B, and then scaling by B, or projecting B onto A, and then scaling by A.
How do you project?
It's the component of A in the same direction as B, scaled by B, or it's the component of B in the same direction as of A, scaled by A.
What if B isn't laying down?
What if B what?
Wasn't laying down. Like, what if it actually had a rise?
Oh, it doesn't matter. So we could have drawn them like this. Same picture. It's just harder for me to do right angles when we draw like that. Try and do it like this. So here's our theta.
So you're trying to make a right angle?
Here's A. Yeah, you always use a right angle when you project. I want to know the component of A in the same direction as B. So trying to draw roughly the same picture here and here. Health angles aren't even close to the same. Same thing though.
Okay.
Make sense?
Yeah.
Okay, that is how we define that operation. Now, it's just so happens to be the case that A dot B is also the exact same thing. This is also equal to the vector AX times BX, or not the vector, sorry, this is a number. It's also equal to AX times BX plus AY times BY. And we'll prove that here in a second, but let's make sure what I said actually makes sense and you know what's written up here. First off, A is the length of the vector A, right?
Mm-hmm.
This is just a number. This is just a number. This is just a number. So notice that this dot product between two vectors spits out a number. Sometimes it's called the scalar dot product because it spits out a number. It doesn't spit out a vector.
Yeah.
Excuse me. Notice over here, real number times real number plus real number times real number. So over here it's also still just a number. So that's the first thing to notice is we're always getting a number. A scalar always spits out a number. A dot product, I mean, always spits out just a number, not a vector. Cross product will spit out a vector. Dot product will spit out just a number. We'll get to cross product a little bit later. Anyways, here's this definition. This is defined to be this, but it's also the same thing as this. We could have also done it the other way. We could have taken this, defined it to be this, and proved it's also the same as this. You just got to pick one and show it implies the other. So it doesn't matter which way you define it. We can pick either way we want to define it and then prove the other thing falls out. You with me? Mm-hmm. So we're going to prove that this gives us this. And it's going to be kind of an annoying bit of algebra. Now before we do that proof, some things to notice. What is I hat dot I hat equal?
Just
1, 0 vector.
same thing.
Oh, no.
It's not a vector, it's just a number. What's the number?
It's a number.
Yes, the dot product gives you a number.
Oh, that's right.
0.
No, 1.
1. What's the length of this vector?
1.
What's the length of this vector?
1.
What's the angle between those two vectors?
Nothing.
0.
Yeah.
So 1 times cosine of 0. just 1.
Yep.
Good?
Yeah.
Similarly, j hat dot j hat is equal to
Well, 1 as well.
1.
Why?
What's the length of j hat?
1.
Length of j hat times length of j hat times cosine of the angle between them. What's the angle between j hat and j hat?
0.
What's cosine of 0?
1.
So 1 times 1. All right, final thing to notice. What is I hat dot j hat equal?
1.
0.
No.
0. There we go.
The angle between-
0.
Okay.
It's 0 because cosine of 90 degrees is 0. That's where the 0 comes from. The length of I is 1, the length of j is 1. The cosine of the angle between them, or sorry, the angle between them is 90 degrees. The cosine of 90 degrees is 0. Geometrically, should be intuitive that that's 0. Here's j hat, here's I hat. Project j hat down onto I hat. That's just a point. Scale a point as big as you want, it's still just a point. Still has a length of 0.
Okay.
Make sense? Just connect some geometric intuition into that. Okay, so with those observations, now we're going to really quickly show that this is the case. So the vector A can also be written as the vector AX I hat plus AY j hat. But then we have to show the dot product can be distributed like that, which we did not show. Should I come at it the other way, or just continue with the book? I'll come back the other way at the end of class if there's time. I don't want to spend time doing it the other way, which is when we define it to be this and show this. But so I'm going to have to do something that we didn't explicitly make clear to you. Oh well. Bx times I hat plus by times j hat. With me? This is the same thing as that. Now, turns out we can distribute that multiplication the same way that we distribute regular multiplication. I don't like that we're doing it this way because how should you know that? Now you just have to take my word for it, sorry. So when we distribute this whole thing out, what are we going to get? We get this times this. So that's going to be AX times BX times with the regular number. So maybe I won't do regular number times. We won't draw any dots. So AX BX I hat dot I hat. I don't want to do squared. I want to make sure that we do the dots for dot product. But you have the right idea.
Yeah.
Okay. And then when we do this one by this one, then that's going to be plus AX BY I hat dot j hat plus, exactly. And then when we distribute this to this, we're going to get AY BY j hat dot j hat plus, and then finally we're going to have AY BY
B hats.
Yeah. Because you already did it by.
Oh, I messed up on my order. Thank you. J hat dot I hat. Right? Okay. And that is equal to, well, I hat dot I hat is just 1. I hat dot j hat, that's 0. I hat j hat dot I hat, that's just 0. So that's 1, that's 1. So that's just AX BX times 1 plus AY BY. With me?
Yeah.
And the algebra gets a lot messier, as you can probably guess, but it works out the same thing in 3 dimensions. if this were in 3 dimensions, then this is still that, but then this is at the same thing as plus AZ times, oh, BZ. Yeah, I did that right. And it comes out the same. It's just you have to multiply 3 terms out by 3 terms, and same observations. Okay. Make sense?
How do you find the cosine of Z?
How do you find the cosine of Z?
Like you want to just show what it looks like when you times the k by k, the k hat by k hat.
So k hat dot k hat is still just 1.
Yeah.
So if we have 3 dimensions, like that, right? And we'll say right here is I hat. Here is j hat. Here is k hat. Right? What's the angle between k hat and I hat? 90. What's the angle between k hat and, what's the angle between k hat and I hat?
90.
What's the angle between I hat and j hat?
90.
So the angles between all of them are still 90.
Okay.
So k hat dot j hat is still 0, k hat dot I hat is still 0, I hat dot j hat is still 0, and then when you dot it with itself, you get 1. Make sense? The algebra just gets hairier,
Yeah.
but it comes out the exact same way. A bunch of your terms, 6 of your terms go to 0, 3 of your terms are remaining as a total 9 terms. Okay, so that is the dot product. Now we have what we call the cross product, the vector cross product. So A cross B is equal to A times B times the sine of the angle between them. Now notice that that's still just a number and not a vector. So you have to memorize a rule for the direction the vector points now. So when I do A cross B, this just gives me the magnitude of the vector. It's a vector with this magnitude, and then it points in the direction perpendicular to these 2 vectors. So cross products we can only do with 3-dimensional vectors. You can't do this with 2-dimensional vectors. This only makes sense with 3-dimensional vectors. And we'll only take cross products in 3 dimensions. We'll never do this in 2 dimensions. This we can do in both. This we'll only do in 3 dimensions. You with me? So, really quick, I take 2 vectors. Pretend we're in 3 dimensions now. The 3rd dimension is going to come straight out of the board. So 2 dimensions will be in the board. The 3rd dimension comes out of the board. You with me?
Okay.
So here's A, here's B, here's A, here's B. I'm drawing terrible. Jeez. There's vector A, here's vector B. And here's the angle between them, theta. I want to find their cross product. Their cross product has a magnitude of the length of A times the length of B times the sine of the angle between them, right? And then what direction do we point that magnitude? We point it perpendicular to both these vectors. You with me?
So that always comes.
So it has to either come out of the whiteboard or into the whiteboard. Now how do we know which way it points? Let me pick one. Actually, that was fine. That was fine. Okay. So how do we know if it comes out of the whiteboard or if it goes into the whiteboard? And now you have to use something called the right hand rule. So you take your right hand. Your first vector that you have listed here, which is A, point your index finger that way.
Any direction?
Whichever way A points. So A points that way, I point my index finger that way.
Okay.
Now, B, the second vector, stick your birdie finger out in the direction that that vector points. Now, whichever way your thumb points is the direction of the cross product.
Is that really how it works?
That's really how it works. It's called a right-handed coordinate system. So, one more time.
Okay.
Point in the direction of A. Orient your birdie finger pointing in the direction of B. Whichever way your thumb points, that's the direction the cross product points. Now, important to notice is that vector A cross B is equal to the negative of vector B cross A. So this is not a commutative property. A cross B is not the same thing as B cross A. It switches directions. So to see that switches directions, let's see that really quick. If I first point my finger in the direction of B, now point my birdie finger in the direction of A, which way does my thumb point? Now it points into the board.
Okay.
Yeah.
Right? When we did A cross B,
Oh, it's your right hand.
point my finger. Yes, you have to use your right hand.
Sorry.
If you use your left hand, you're going to get really confused. This is also why it is very, 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 very important. Anytime you are drawing a picture for 3 dimensions, you draw your picture like this. Your coordinate system. You need to always call this one your X, this one your Y, and this one your Z. You don't necessarily have to do that, but if you don't do that, you don't have what we call a right-handed coordinate system. So if I switch my X and my Y here, that's bad. We no longer have a right-handed coordinate system.
Okay.
It's a right-handed coordinate system. Basically, if it follows our... Oh, no. Did I do it wrong to begin with? X is here, Y is here, Z is there. I don't know if that's how I had it before. This is the way to show I was having it.
Okay.
I'm not sure if I screwed up before. And it's set up so that if you point your index finger in the X direction, your birdie finger in the Y direction, then your thumb always points in the Z direction.
I see.
So it's called a right-handed coordinate system. And you will get in all sorts of weird problems if you forget to do this and if you accidentally call that X and that Y. Because then you have a left-handed coordinate system.
Yeah.
And it's going to confuse you. Now, there's nothing wrong with using a left-handed coordinate system. All the math can come out fine. It's just you're most likely going to run into weird problems that you can't figure out where your signs keep coming off because you just drew your picture weird. So, always a forever draw your picture like that. Anyways, so does that make sense? A cross B is the negative of B cross A.
Yeah.
Changing which you cross with which changes whether it points in or points out.
What?
Let's do A cross B one more time.
Okay.
Point my finger in the direction of A. Point my birdie finger in the direction of B. My thumb points out of the whiteboard.
Yeah.
Now, let's do B cross A. Point my finger in the direction of B. Point my birdie finger in the direction of A. My thumb points into the whiteboard. So they point opposite directions. Same vector, opposite directions. A cross B and B cross A give you the exact same vector but opposite directions. So they're the negative of each other. Because the magnitude's the exact same.
But they're equal to each other?
Same magnitude, opposite directions. Does that make sense?
Mm-hmm.
Okay. One more way that you can calculate this, you can do AB sine of the angle between them. Sometimes when we're in 3 dimensions, it's kind of hard to find the angle between 2 vectors. Right? If you think about my arms being vectors, so we got one vector pointing like that and another vector maybe pointing like this, finding the angle between those 2 vectors is sometimes a pain. It's easy when they're both just flat in the whiteboard. It's harder when one's sticking out weird and one's in the whiteboard. You can do it, and we'll come up with ways of doing that. You don't need to worry too much about right now. But since that's hard, generally, it's more difficult, there's another way that we can calculate this value. And I'm not going to prove that we can calculate this way. I'm just going to give it to you. And that is to calculate a determinant. You remember that word? Determinant?
A little bit.
Little bit. Okay, a determinant. Since Peter's never done this, a little bit of college algebra coming at you. Or, yeah, college algebra.
Okay.
So we set up a determinant. In the top, it's like a matrix. It's going to be a 3 by 3 matrix. In the top row, we write I hat, J hat, K hat. Because we can only take cross products with 3-dimensional vectors. Doesn't make sense to do it with 2-dimensional vectors. Has to be a 3-dimensional vector. Next row, we write all the components of our first vector. Next row, we write all the components of our second vector. Make sure I'm following this, how the book does it. Because I think we can also, yeah, that's how the book does it. We could have also, doesn't matter how we could have also done. This is good enough. Okay, calculating a determinant. First, let's calculate a determinant in 2 by 2 case before we go to 3 by 3. And let's just do a simple example. 2 by 2 case of calculating a determinant. These are going to be numbers, these are going to be vectors, but let's just start simple. Imagine I have 1, 5, 7, 2, and I want to calculate what we call the determinant of that. Here's how you do it. You take the product across the diagonal here and subtract the product across the diagonal here. So this is equal to, the product across the diagonal is 2 minus the product across the diagonal is 35. Okay? Another one, just to make sure we're clear. 7, 9, negative 2, negative 1. Tell me what to write.
Negative 7 minus negative 18.
Perfect.
Okay.
That's how you do a 2 by 2 determinant. A 3 by 3 determinant is more complicated. When we do a 3 by 3 determinant, we turn it into a bunch of 2 by 2 determinants. So I'll just show you here with the 3 by 3 determinant. We go across the top row, we take the first number, and we write that number. And then we look at, ignore the row and the column that it's on, and that gives you just 4 numbers now, right? A 2 by 2. So we multiply it by that 2 by 2 determinant. AY, AZ, BY, BZ.
Okay, I see.
And we do that all the way across. So then we add on, is it plus minus plus? Or do you just always plus? Can't even remember, it's been so long. Oh, I guess we could do it that way. Sorry, we can algebraically show this rather than using algebra that you haven't seen before. Let's just calculate it. And show that it's going to be the same as the result that you get from the determinant. So this is also equal to, I shouldn't have erased the picture there because it would help me write the answer so I don't have to keep looking at the book. If you want to know how to calculate a determinant, you can just go look it up real quick. It's not that hard, I'm just not sure I want to take all the time to go through it. Okay, so really quick, what's going to come out to is we're going to have this number here is going to be AY times BZ minus AZ times BY. Maybe make sure I'm not thinking about anything weird. Oh, that's how he's going to specify it, so that we don't make a huge mess. So let's say that C is equal to that vector. You with me?
Yeah.
Okay, so then Cx, here's another way that we can do it. Cx, its x component, is going to be AY times BZ minus AZ times BY. Its y component is going to be AX times BZ minus AZ times BX. And I can't remember if you're throwing negative in there or not, so let's see if that's the same signs. Yeah, we're good. Okay, And then CZ is going to be AX times BY minus AY times BX. Actually, we can explain the algebra now that we have this written out. Probably should have just written it out and showed it. So notice that the component in the x direction or the component in the I hat direction is the determinant when you ignore the row and column that I hat's on. So ignore this row, ignore this column, it's the determinant of this. That times that minus that times that. Okay. For j hat, same thing. Ignore the row and the column that j hat's in. And now calculate the determinant. That's going to be ax times bz minus az times bx.
Yep. And
then finally, for c, for the in the k direction, same thing. Make sense?
Yeah.
Okay. Maybe it's not worth writing all the algebra to prove this, but we can show that this gives us all this algebraically, same thing we did with the cosine. The trick is to notice with your I hats and your j hats what happens. So the trick is just to notice what is I hat cross I hat equal.
1.
It is, well, what's your sign?
What's the magnitude of I hat?
1.
What's the magnitude of I hat?
1.
What's the angle between I hat?
0.
What's the sign of 0?
0. Okay, I see.
Similarly, what is I hat cross j hat equal? 1.
So it's at 90.
Perfect. So if we were to write A as its 3 components and cross product them with B written out as its 3 components, we would have 9 terms. 3 of those terms are going to go to 0. The remaining 6 terms are going to give you these 6 numbers. That's how it would come out if you did all the algebra. And I don't think there's any point in seeing all that. Your book has it written out if you want. Good?
Yeah.
Okay, that is the end of chapter 1 of physics. Now we did a bit more depth in vectors than your book does, so hopefully you're not too overwhelmed with the homework, because I'm sure that was a lot to swallow.
Okay.
What's the homework?
So get started on your homework. You should have syllabuses.
It's just chapter 1,
Yeah, just chapter 1 homeworks due tomorrow, and we'll start chapter 2. And again, strongly recommend going through the material yourself. Not as much of a big deal for chapter 1 because there wasn't really physical concepts to cover, but with chapter 2 we're going to start covering physical concepts. Chapter 2 should still be real easy for you guys because we did a lot of chapter 2 and chapter 3 in physics, or in calculus already. So it's not till chapter 4 that you're going to get real new physical concepts.
Alright.
But one of the reasons it's worth reading through and just looking at the math is because you're not used to doing math with vectors now, or derivatives of vectors, or integrals of vectors.
and we're going to be doing that a ton.
And you're going to be doing that a ton.
Okay.
Now it's not super hard. Maybe we can really quick show you how to do that. Imagine I have some vector, and the x component of my vector is 3t, and the y component of my vector is 2t squared. So this gives you my, my position vector at any time t. You with me?
Mm-hmm.
So if this is my position vector, so x of t, there's my position vector. Then now what's my velocity at any time t? You still just take the derivative, you just do the derivative of each component. It's 3 and then 4t. Just taking the derivative. And then what's my acceleration at any time t? It's just 0 and 4. So you just take the derivative of each component.
Okay.
Okay.
That's the only difference with working with vectors versus working with real numbers. It's easy, but when you look at the notation in the formulas, it's going to be hard for your brain to wrap your head around it the first time. So that's why it's good for you to just try and read the formulas and understand the formulas.
So you're
Because
saying,
get used to reading vectors and working with vectors. That's going to be the big change.
you're saying to pre-read it before we come to class?
For chapter 2, I recommend it. Or at least look over the book everywhere that you see a formula and make the formula make sense in your head. Because they do a good job highlighting the formulas in this book.
A lot of words.
It's a lot less than it looks like. So for example, on this page, there's nothing for you to read. This is an example problem, and then this is nonsense that they put in modern textbooks. This whole thing right here is an example problem. Here's actual text, example problem, example problem. Here's actual text, example problem, example problem. Here's actual text. So you can cover a lot of pages without much reading. But it is going to be a decent amount of reading, so I don't want to mislead you.
Okay.
But the book is misleading in how thick it is.
Are we
Anyways.
good to take a break?
Good. Yeah, we're done. So.